Section 10.5, multiplying and dividing radical expressions. Last time we looked at adding and subtracting, which wasn't too bad at all. This section is a little more intense, and we're just going to start with some homework problems. Multiplying radical expressions, we already have all the tools that we need to be able to work these. Let's look at number 8. To multiply, we're going to distribute this square root of 10 to each of the two terms inside the parentheses. Square root of 10 times 5. The 10 is inside a square root. The 5 is outside of a square root. So the 10 and the 5 can't see each other. This is simply 5 times the square root of 10. 5 square roots of 10. And minus the square root of 10 times the square root of 3. Well, those are both inside. The 10 is inside, the 3 is inside. Square root of 10 times square root of 3, we know from our product rule, is the square root of 10 times 3. And so that's simply the square root of 30. Insides can get together. Outsides can get together, insides can get together, but insides and outsides cannot see each other. Square root of 10 times square root of 3, square root of 30. Check to make sure that you don't have any perfect squares under a square root. 10 is what? 2 times 5? No pairs there, no perfect squares. 30 is 2 times 3 times 5. 2 times 3 times 5. No pairs. So no perfect squares contained in that 30. And so this is simplified. Let's look at number 10. Now here in number 10, hopefully you've already spotted that 50 contains a 25. 18 contains a 9. And you can deal with that now, or you can deal with it later. Let me work this one both ways. If we deal with that later and start by just distributing this 7, the 7 is outside of a square root, the 50 is inside of a square root, so as I distribute to this first term, I get 7 square roots of 50. Minus 7's an outside, 18 is an inside. They cannot see each other. That gives me 7 square roots of 18. Now I have to deal with the fact that both of my radicands contain perfect square factors. This 50 contains a 25. It's 25 times 2. Square root of 25 is 5. The 2 is stuck inside. And so this is 35 square roots of 2. Minus 18 contains a 9. It's 9 times 2. Square root of 9 is 3. The 2 is stuck inside. And 7 times 3 is 21. And it turns out that these are like radical terms. So we will go ahead and subtract by combining like radical terms to get a difference of 14 square roots of 2. Let me go back and work this again, this time dealing with my perfect square factors in my radicands right away. 14 square roots of 2 is the answer. This time, let's go ahead and notice our 25 contained in the 50. Notice our 9 contained in the 18. Square root of 25 is 5. Square root of 9 is 3. Now, two ways to proceed from here. You could go ahead and distribute. That's not what I'm going to do. But if we did, well, let's go ahead and do that and just see it. We'll see it 3 different ways. Distribute the 7, and we get 7's on the outside, 5 is an outside, that 2 is an inside. Outsides can see each other, insides can see each other. 7 times 5, those are both outsiders, so we get 35 square roots of 2 minus, distributing to our second term, the 7 and the 3 can see each other, they're both outsiders. 7 times 3 is 21, and that should look familiar. That was our next to the last step last time. And again, combining like radical terms, 14 square roots of 2. But I think probably the slickest way to work this problem is to deal with those perfect squares under the square root first, and then notice here in parentheses I have like radical terms. Go ahead and subtract them. 5 square roots of 2 minus 3 square roots of 2 is 2 square roots of 2. Multiplication is associative, so I can drop those parentheses. I have 5 times 2 times the square root of 2. I'm sorry, 7. 7 times 2 times the square root of 2. The 7 and this 2 are both outsiders, so they can see each other. 7 times 2 is 14, and we've got that square root of 2 tagging along at the end. This is probably the slickest way to work this problem. All right, number 18. The thing to notice on that last problem, though, is no matter how I worked it, I got the same answer because at no point in any process did I break the rules of algebra. Now here in number 18, we've got 2 terms times 2 terms. I don't call these binomials because they're completely numeric. But they're going to behave just like multiplying binomials. We need to FOIL this. We're going to use FOIL to multiply this out. Product of the first, square root of 3 times square root of 5. The 3 and the 5 are both insiders. So that's going to give us square root of 3 times 5 is 15. The outside, watch your signs. Positive times a negative is negative. That 3 is an insider. That 2 is an outsider. So I simply get 2 square roots of 3. The 3 and the 2 can't see each other. That's not really a 3 anyway, is it? That's some crazy irrational number, 1.732, etc., etc. That's some crazy irrational number. So we have no business trying to get that 2 and that 3 together. Product of the inside. Well, 3 times square root of 5 is just that, plus 3 square roots of 5. And product of the last, 3 times negative 2, minus 6. None of these are like radical terms. No radicand contains any factor which is a perfect square. And so that's simplified. Let's try another one of these FOIL problems with number 22. We're going to FOIL this, and so product of the first, square root of 7 times 2 square roots of 7. The 2 is an outsider, and the 7's are both insiders. Square root of 7 times itself, though, is what? Square root of 7 times square root of 7 is just 7. Because why? The square root of 7 is that number that when multiplied times itself will give you 7. So you multiply it times itself, it gives you 7. If you need to be reminded, square root of 7 times square root of 7 is the square root of 7 times 7, square root of 49, which is back to that 7. But I want you to get used to seeing a square root times itself and knowing it's just the radicand. Square root of 7 times itself is just 7. We'll do that again in a minute with the 11s. Let's go on. We'll clean this product up in a minute. Let's go on and do the outside. Square root of 7 times 3 square roots of 11. The 3 is an outsider. He's all by himself. And square root of 7 times square root of 11. 7 and 11 are both insiders this time. That's going to be the square root of 7 times 11, or the square root of 77. Product of the inside. Watch your signs. This was going to be minus. Get your outsiders, just that 2. Square roots of, get your insiders. 11 times 7, 77. And then finally, product of the last. Watch your signs. It's going to be minus. Your outsider is just that 3. And what do we have here with our square roots? Square root of 11 times itself is just 11. Let's clean up these products first. That's a 14. And that's a minus 33 there at the end. Now combine like terms. Our numeric terms, 14 minus 33 leaves me a negative 17. No, it doesn't. 14 minus 33 is going to leave me, I just went completely blank on that, a negative 19. There we go. And then our like radical terms, we have 3 square roots of 77 minus 2 square roots of 77 leaves me plus 1 square root of 77. We don't write the 1. 77 is just 7 times 11. There's no perfect squares hiding in that. And so this is simplified. All right. Let's have a look at number 34. Another FOIL problem, but this one has an interesting result. And speaking of interesting, have a glance at number 29 while I get this written up here. Number 29, you've got 2 terms times 3 terms. You're going to have to do what to work number 29? Term by term multiplication. Distribute each one of these to every one of those. So that looks like fun, but I'll leave that to you in the homework. If you have fits with number 29 and want an additional problem to work, number 30, just holler at me for the answer to number 30, and I'll be happy to provide you with that. All right, number 34. We're going to FOIL this out. Product of the first. Square root of k times itself. Well, that's just k. And notice in the instructions she has said that all variables represent positive real numbers. We don't have to worry about absolute values here. Square root of k times itself is just k. Now the outside, it's going to be minus. The 4 is an outsider. The k and the m are both insiders. So minus 4 square roots of km. Product of the inside, as we continue to FOIL, is going to be plus 4 square roots of km. And product of the last, 4 times negative 4 minus 16, there's your outsiders. And your insiders, square root of m times itself, well, that's just m. Combine like radical terms. And we should have expected this to happen, Do you recognize this pattern? The product of a sum and difference of the same two terms? So we would expect this to happen because we know that when we have a first plus a last times a first minus a last, we always get simply first squared minus last squared. That's one of our rules from back in chapter 4. We FOILed it out completely. Our inside and outside terms are going to subtract out. Minus 4 of them plus 4 of them leaves none of them. So we end up with just what? This k up front and this minus 16m from the end. Now if we had noticed that this was the product of a sum and difference, we could have used our special product rule and just said, oh, it's going to be the first squared. What do you get when you square the square root of k? You square the square root of k, you get just k. Square and a square root undo each other. Minus, always minus, and the last squared. You square this last, you square 4 to get 16, you square the square root of m to get just m. And that's how we're going to want to do these in some of these later problems here toward the end of the section. We're going to definitely want to take advantage of our special product rule. Number 36. Make sure that index is tucked nicely in to that check mark, so I know it's an index and not a power, say on this 5 right here. I don't want to think that that's 5 cubed. Make it very clear that that 3 is the index of your radical. And again, we have a FOIL problem. Product of the first. 5's an outsider, so we've got 5, and then my cube roots. 9z times 9z. Cube root of 81z squared. 5 was the only outsider. The 9z's are both inside the radical. And so we multiply those using our product rule for radicals to get cube root of 81z squared. Now the outside. 7's an outsider. Everything else is an insider. This is plus 7 cube roots of 9z. Product of the inside. Watch your signs. Minus my outsiders. 2 times 5 is 10. And times that cube root of 9z. And finally, product of the last, as we finish our FOIL. Minus 2 times plus 7 is minus 14. We'll combine these like radical terms, but there's something else we don't want to forget. We've got to check and make sure that each of these terms is simplified. These last 3 terms are simplified, but look at this first term. 81 under a cube root. 81 is 3 to the 4th, so you know it contains a 3 cubed. In fact, let me just write it right here. 81 is 27 times 3. So I'm just going to use a little shorthand here to save me a step. 81 is 27 times 3. So what do we have? We've got our 5 out front. The cube root of 27 is 3. And this 3 has to stay inside, along with the z squared. And we're going to deal with that product here in just a minute. Now, do you understand what has happened here? I replaced the 81 with 27 times 3. took the cube root of that 27 to get this 3. Then this 3 and that z squared, they're stuck inside. All right. Combining like terms here in the middle, 7 of them minus 10 of them is minus 3 of them. And finally that minus 14 at the end. Then just clean up this front term. 5 times 3 is 15. 15 cube roots of 3z squared minus 3 cube roots of 9z minus 14. Each term is simplified. There are no like radical terms left to be combined. And so that's done. So that's multiplying radical expressions. We're going to turn our attention now to dividing radical expressions. An example might look like this. Let me just make one up. 3 divided by the square root of 2. How do we go about dividing that? Well, it's not going to be division as we normally think of it. It's not going to be our usual type of division. It's going to go back to this rule of simplification in section 10.3. So join me, if you will, on page 672, and let's reread our conditions for a simplified radical. Number 1, the radicand has no factor raised to a power greater than or equal to the index. What do we say that meant? That meant no perfect squares under a square root. So we simplify square root of 50 to 5 square roots of 2. That's our first rule. The second rule says the radicand has no fractions. We've seen some of those. And how do we deal with that? We split it apart. And the bottom, of course, square root of 25 is 5. Let's jump down to number 4. In number 4, it says, the exponents in the radicand and the index of the radical have greatest common factor 1. This index and this power have a common factor of 2. And we do have our rule over here on page 674 that says we can simply divide the index and the power by that common factor, divide them both by 2. That would give me a square root of z to the first, or just square root of z. I've been encouraging you to take this through your fractional exponents and witness the reducing of that fraction. I mean, that's the whole reason that this rule works from page 674, is because we are actually reducing a fraction. But now let's re-examine this third rule of simplification. And I said we would come back and talk about this another day. Well, this is the only day we have left, so we're going to talk about it. Number 3, it says no denominator contains a radical. That's a problem with the one here on the board. No denominator contains a radical. So what do we do with this? Well, we just kind of noticed in some of the previous problems that a square root times itself gives you just what's inside. And so if I could multiply this square root of 2 times itself, I'd be in business. Well, I can do that so long as I what? Multiply also the top by the square root of 2. That way I'm just multiplying by what? A big blue 1 here. Square root of 2 over itself, that's just 1. I'm multiplying by 1. I'm going to change the way this looks, but I will not change its value. Multiply the tops. 3 is on the outside, 2 is on the inside, so 3 square roots of 2 over square root of 2 times itself is just 2. And I have no radical in this denominator. This is called rationalizing the denominator. And we have a blue box here on page 690 that we want to look at. Rationalizing the denominator. Page 690, middle of the page. It says a common way of standardizing the form of a radical expression is to have the denominator contain no radicals. So this is an idea like we always reduce fractions to lowest terms. That way I don't have the answer 2/4 and you have the answer 3/6 and somebody else has 5/10 and we're all trying to compare, hey, did we get the right answer? If we all reduce our answer to lowest terms, we all have the same 1/2. Well, that's what she means by standardizing here. Okay? These two expressions, 3 over the square root of 2 and 3 square roots of 2 over 2, they have the same value. But if you write this as a final answer and I write that as a final answer, it makes it hard to compare. So we're standardizing, we're agreeing on a certain way to write our final answers. It says the process of removing radicals from a denominator so that the denominator contains only rational numbers, no radicals, so only rational numbers, is called rationalizing the denominator. And she says this is done by multiplying by a form of 1. That's our thing in blue here. Square root of 2 over 2, that's just 1. Something times 1 is itself. We changed the way it looks, but we did not change its value. Rationalizing the denominator. Join me once again in the homework. And we'll look at number 44. Now, once we have our answer, I want to come back and think about this guy. What is the square root of 11 divided by, what is 11 divided by the square root of 11? But let's look at this right now. As the instructions say, rationalize each denominator. And once again, we assume variables represent positive real numbers. I might say rationalize the denominator, or I may only say what? Simplify. Because to simplify includes now rationalizing these denominators. That third rule from our simplification of radicals said we can have no radicals in a denominator. To get rid of a square root of 11, I'm going to multiply by the square root of 11. I have to do that top and bottom so that I'm not changing the value of my original fraction. Multiply the top and bottom by the square root of 11. In the top, this 11 is on the outside, that 11 is on the inside, so we have 11 square roots of 11. In the bottom, square root of 11 times itself, well, that's just 11. Now think back to chapter 6, where we're simplifying rational expressions. If you had 11x over 11, what would you do? You'd cancel the 11s, and your answer here would just be x. Well, that's exactly how this behaves. I have a factor of 11 in the top, a factor of 11 in the bottom, and they will cancel to leave just the square root of 11. Now, I said I wanted to come back and think about this. The 11 divided by its own square root. Does it make sense to you that 11 divided by its own square root, that the answer is its own square root? Well, how do you check a division problem? If I said, what is 10 divided by 5? You'd say, well, that's 2. And how do you check that? You check a division problem by multiplying. Is it true that 2 times 5 gives you back that original 10? Yes. And so, how will I check this? Now, I'm not recommending this as a way of checking the problems necessarily, but it will work. It can get messy sometimes. But you can always say the answer times the original divisor had better give you back the original dividend. Square root of 11 times itself is 11. So yeah, that makes perfect sense. All right, let's move on. Number 46. (12 over the square root of 6). Like I said, we're not dividing in that traditional sense. We are simplifying by rationalizing this denominator. We'll rationalize this denominator, multiplying the top and bottom by the square root of 6. In the top, we have 12 square roots of 6. That 12 and 6 can't see each other. 12 is an outsider, 6 is an insider. And in the bottom, square root of 6 times itself is 6. Can this be simplified any further? Well, not as far as radicals go, but as far as rational expressions, I can reduce this. 6 goes into 12 twice. This reduces to 2 square roots of 6. And like I said, you can always check these. Is it true that this answer times that original divisor, does that give you back the original dividend? Well, this is 2 times square root of 6 times itself is 6, and 2 times 6 is 12, and so that does check. So you do have a method of checking these. Just always make sure that your final answer is in simplified form. As far as the radicals go, as far as fractions go, we have many, many rules of simplification to work with now. We've been adding to them since the beginning of the semester, so keep them all in mind. Number 52. Now, if you like, you can multiply the top and bottom of this by the square root of 24, and you will end up with the right answer. However, there's an easier way to go about this. The first thing I'm going to do is recognize that 24 contains a perfect square, contains a 4. I can simplify this radical before I rationalize the denominator. That 24 contains a 4, and so this denominator simplifies to 2 square roots of 6. Now let me rationalize this denominator. And the only thing I'm worried about is my square root. So the only thing I need to multiply by is the square root of 6. In the top, we get negative 5 square roots of 6. In the bottom, we have this 2 as an outsider. And square root of 6 times itself is 6. So we finally get negative 5 square roots of 6 over 2 times 6 is 12. A common mistake here is to try to simplify this further, canceling 6 into 12. One of my wrong answers on a multiple choice test might be if someone said, well, 6 goes into 6 once, square root of 1 is 1, and 6 goes into 12 twice. Why can't we do that? Because that 6 is an insider, he's inside the square root, and that 12 is an outsider. In other words, that's not a 6. That's some crazy irrational number. That's some 2 point, I don't know what. But it's some crazy irrational number. So we can't go canceling a 6 into that 12 because we don't really have a 6 to begin with. We have a 2 point, I think it's 2.235 approximately. But it's some irrational number. And so you cannot reduce that any further. That is simplified. Let's look at number 56. Number 56. One of our rules of simplification says that we are not allowed to have a fraction under the square root. Well, we know how to fix that. We'll use our quotient rule for radicals and write this as negative the square root of 13 over the square root of 75. Okay, so we no longer have a fraction under our radical. However, we've got a radical in this denominator. So, we need to deal with that. We need to rationalize this denominator. And the first thing I'm going to do, like we did in the last problem, is I'm going to notice that this 75 contains a factor of 25. We've got this floating negative that's going to be with us the whole time. But the first thing I want to do is get my numbers smaller and easier to work with here. 75 is 25 times 3. So we've got negative square root of 13 over square root of 25 is 5, and that 3 is stuck inside. Now we can look at rationalizing this denominator. We're going to multiply the top and the bottom by that square root of 3. We've got our floating negative out front. Square root of 13 times square root of 3. Those are both insiders. Our product rule for radicals says that's the square root of 13 times 3, or the square root of 39. In the bottom, that 5 is an outsider. Square root of 3 times itself is just 3. And so we have square root of 39 over 15. Don't forget that floating negative out front. Check to see that the numerator does not need simplified any further. 39, you know, is 13 times 3 from the step above. And so this is simplified. 39 contains no factor, which is a perfect square. Just a moment ago, I said the square root of 6 I thought was about 2.235. I've been pondering that this whole time. No, that's the square root of 5. Square root of 5 is about 2.235. Square root of 6 is about 2.449. So I got those switched. That's been bugging me this whole problem. I don't want to tell you the wrong thing. In that last problem I said we don't actually have a 6. We've got a square root of 6, which is some crazy irrational number. Well, here's the approximation. It goes on forever. Never repeating, never terminating. Just want to be straight on that. All right. Moving on now to number 58. I just don't want to tell you the wrong thing. She said all variables represent positive real numbers, so we don't have to worry about, in this case, something being square root of a negative, which would be not real. We can expect y to be a positive number. Well, our problem here is we have a fraction under the square root. That's an easy fix with our quotient rule for radicals. Split it up. Square root of the top over square root of the bottom. That creates a new problem. We now have a square root in this denominator. So we'll rationalize multiplying the top and bottom by the square root of y. In the top, these are both insiders, so we could put them together. Square root of 52y. And in the bottom, square root times itself, square root of y times square root of y, is just y. Now, careful with this one. Always check to make sure that your answer is completely simplified. This one is not. Do you see why? 52 contains a factor of 4. 52 contains a factor of 4. 52 is 4 times 13. I notice that because I'm a big poker player. And to me, 52 is a deck of cards. And in that deck of cards, there are 4 suits with 13 ranks each. So that 52 always jumps out to me. Whether it jumps out or not, you've got to find it. You've got to spot it. Because this step here at the bottom of the board is not simplified. We'll finish this off by saying the square root of 4 is 2. We have 2 square roots of 13y all over y. And that is our final answer. Number 62. This is another one of those sections where we don't have a lot of new information, but we do have a lot of different ways to use that information. And so we want to work lots of examples. In number 62, we have a fraction under the square root. Don't forget your floating negative. We can fix a fraction under the square root with our quotient rule for radicals, square root of the top over square root of the bottom. Now, both the top and the bottom separately can be simplified further before we even consider thinking about rationalizing this denominator. You could multiply the top and bottom right now by the square root of square root of s to the 5th. But I think it'll be easier in the long run if we boil this down some first. This radicand in the numerator contains a perfect square. Not only an r squared, but in this 98, there's a 49. 98 is 49 times 2. R cubed contains an r squared. It's r squared times 1 more r. Let's come back to that in a minute. In the bottom, s to the 5th contains s to the 4th. And so, we have our floating negative, don't lose him. Square root of 49 is 7. Square root of r squared is r. Since we know r is positive, we don't have to worry about absolute value marks. And our 2r is stuck inside. Over, right here, square root of s to the 4th is s squared, leaving an s inside. Now we want to think about rationalizing this denominator. We can do that multiplying the top and the bottom. I'll squeeze it in here by the square root of just s. That's all we need to rationalize is this square root of s. So we've got our negative. We've got our 7r. And square root of 2r times square root of s is square root of 2rs. Over, we've got our s squared, and the square root of s times itself is just s. So finish this off by cleaning up this denominator. We've got our negative, our 7r, square roots of 2rs, and in the bottom, s squared times s is s cubed. Number 66. This might be one that you want to try on your own and see how you do. Come back and we'll compare answers. I would recommend first simplifying that denominator before you consider rationalizing that denominator. Go ahead and pause here, give this one a try, and come back and we'll compare answers. This one's actually not too bad. I'll simplify this denominator first, and you can do it like we did the last problem and write that as m squared times m. I'm just going to very quickly use our long division with remainder, where I can say 3 divided by 2 is 1, remainder 1. 1m on the outside with 1 remaining inside. You'll get the same thing if you do that the longer way, of course. Now we'll rationalize the denominator, multiplying the top and bottom by the square root of m. Multiplying in the top, we've got our 2 on the outside. Our insides will give us 5rm, or if you prefer, 5mr would be just fine. Over, we've got this m from the outside. Square root of m times itself is another m. Okay? Are you with me on this? This m on the outside just gets copied down. And then this square root of m times itself gives me the other m. And so finishing this off, we have 2 square roots of 5rm over m times m is m squared. Not too bad. How'd you do? Now, I'm going to continue this lecture, but I might suggest here that this might be a good time for a break. You might want to take a break from this. Go ahead and try some of the homework up through number 67, and then come back, because we're about to switch gears. We're going to do some cube roots, and we're going to do some denominators that have more than one term. So we're going to be shifting gears. You may want to pause here, make a note of the timestamp on the video, and then come back and join me once again as we continue with the next batch of homework problems. Whether you're coming back from taking a break or continuing along with me through the rest of this lecture, I want to look now at problems where we have a cube root in the bottom. Let me just make up a couple. Cube root of 2. Well, if I multiply the top and bottom, don't do this. If I multiply the top and bottom by the cube root of 2, it doesn't get me anywhere. That's going to give me a cube root of 2 over a cube root of 4. And cube root of 4 doesn't simplify any further. So that does not rationalize the denominator. What I need to do is multiply the top and bottom by the cube root of something that will turn that 2 into a perfect cube. Well, the smallest perfect cube that contains 2 as a factor is 2 cubed, or 8. To turn 2 into an 8, I'll need a cube root of 4. In other words, think of it this way. I have a single 2 here. I'm multiplying it by a couple more 2's. I have 3 of a kind. I'm looking for 3 of a kind to be under this cube root. Now I get cube root of 4 in the top over, that's the cube root of 8, and the cube root of 8 is 2. Cube root of 4 over 2. And so that's rationalized. Let's consider another problem. How about 7 over the cube root of 4? Multiplying top and bottom by cube root of 4 isn't going to get me anywhere. What I'll do is I'll say, what is the smallest perfect cube that contains 4 as a factor? And I think an easier way to do that is to say, what is this for? It's a pair of 2's already. So what do I need? I need one more 2. I need to multiply the top and bottom by the cube root of that one more 2. Because now, in the bottom, that will give me a cube root of 8. In the top, it's 7 cube roots of 2. In the bottom, it's a cube root of 8, which is just 2. Remember, this 2 on the inside, this 2 on the outside, they can't see each other. Don't reduce. Same for this 4 and that 2. That's not really a 4. That's a cube root of 4. Some crazy irrational number. So don't try to cancel insides and outsides. With those 2 examples, let's look at number 70. The first problem is we have a fraction under our cube root. We can fix that by splitting this with our quotient rule for radicals. Now we need to figure out, what are we going to rationalize with? Well, we already have a single 5. We already have a single 5. So what do I need to make this 3 of a kind? I need a couple more 5's. I need a 25. Multiply the top and bottom here by the cube root of 25. So in the top, I'll end up with cube root of 4 times 25 is 100 over the cube root of 5 times 25 is 125, which of course is a perfect cube because we designed it that way by finding 3 of a kind. Cube root of 100 over, and then the cube root of 125 is simply 5. And that's simplified. 100 contains no perfect square factors. I know that just looking here. It's what? A pair of 2's and a pair of 5's. You see what I'm saying? 100 is a pair of 2's and a pair of 5's. So I know it does not contain any perfect cube. It does not contain a 3 of a kind. Let's look at number 72. We have a fraction under the radical. So we'll fix that with our quotient rule. Cube root of the top over cube root of the bottom. And I do not want to multiply the top and bottom, if I don't have to, the top and bottom of this by the cube root of 16 squared to get my 3 of a kind. Actually, do you see what I want to do first before I even think about rationalizing this denominator? The first thing I want to do is simplify this radical in the denominator. 16 is 8 times 2. 16 is 8 times 2. Cube root of 8 is 2, and the other 2 stuck inside. Cube root of 16 becomes 2 cube roots of 2. Now let me rationalize. Multiply the top and bottom here by the cube root of, you know what we want to use here, right? We've got a single 2 under our radical already. We're looking for 3 of a kind. We need another pair of 2's. That's a 4. In the top, we multiply to get cube root of 20. In the bottom, we have this 2 on the outside, and we multiply our cube roots together. Cube root of 2 times cube root of 4 is cube root of 8. Cube root of 8 is just 2. And now in the bottom, 2 times 2 is 4. I'm showing all these steps for the sake of our notes. Some of you may be at a point already where you say, oh, cube root of 2 times cube root of 4, that's cube root of 8 is 2. You may not put this step. Some of you are going to appreciate putting all the steps in so that you don't make some silly mistake. So it depends on previous experience and depends on your comfort with these types of problems, the number of steps you end up putting in. For the sake of our notes, I'm putting them all in, and I'm still recommending that you put them all in. Let's look at number 74. Fraction under a radical. Split it. The top and the bottom in and of themselves are both already simplified. I want to figure out what I'm going to use to rationalize this denominator. 9 is already a pair of 3's. So what do I need to get 3 of a kind? One more factor of 3. Let me multiply the top and bottom here by the cube root of that one more factor of 3 that I need to get my 3 of a kind. So in the top, we'll get the cube root of 30. In the bottom, cube root of 9 times 3 is 27. And the cube root of 27 is 3. Number 76. We've got a floating negative that's going to tag along. We have a fraction under a radical. Let's use our quotient rule to split that apart. Cube root of 6x over cube root of y squared. Let's figure out what we're going to rationalize with. I already have a pair of y's. I need 3 of a kind. So one more factor of y will do it. Multiplying the tops, let's not forget our floating negative. Multiplying the tops, that's going to be the cube root of 6xy. And in the bottom, some of you are ready to write the final answer right now. I'm going to show this step, and then I'll write my final answer. This is going to be what? The cube root of y squared times y is y cubed. And then, of course, the cube root of y cubed is just y. We have our floating negative, our 6th root of xy in the top, and over cube root of y cubed, just y. And that denominator is rationalized. Let's do one more of these, this time with a fourth root, number 82. So now we're not looking for a pair, we're not looking for 3 of a kind, but we will be looking for 4 of a kind as we try to rationalize a denominator that has a fourth root. We'll split this using our quotient rule for radicals, taking care of that fraction under the fourth root. Now we've got to deal with this radical in a denominator. We need to rationalize this denominator, multiplying the top and bottom by the fourth root of something that will give me a 4 of a kind. I already have 2 factors of s. What do I need? 2 more factors of s. And there's my 4 of a kind. If this had been a single s, I'd use an s cubed. If this had been an s to the third, I'd use a single s. I'm just trying to get 4 of a kind under my radical here in this denominator. Multiply top and bottom by the fourth root of s squared. In the top, that'll give me fourth root of 7t s squared, or 7s squared t if you prefer. In the bottom, that's the fourth root of s squared times s squared is s to the fourth. And the fourth root of s to the fourth is simply s. We're going to shift gears one more time as we now look at the problem starting with number 83. I'm going to grab number 84. Now let me show you something that won't work. Multiplying the top and bottom here by the square root of 6 won't work. In the top, you'll get 4 square roots of 6. In the bottom, you will have to distribute, which will give you 5 square roots of 6 plus square root of 6 times itself is 6. Yeah, you got rid of this square root, but it created another square root. So that doesn't work. Look back at number 34. The idea that we saw there in number 34 is going to get us through this problem. If we multiply the sum and difference of the same 2 terms, it will give me the first squared minus the last squared. And something squared, a square root squared, that gets rid of a square root squared gets rid of a square root. This should have no square roots in it. If we multiply the top and bottom here by 5 minus the square root of 6, I should be left with no square roots in the bottom. Now this first time through, I'm actually going to ignore my special product rule, and I'm actually going to FOIL out the bottom and just show you one time. But the rest of the time, we're going to want to use our special product rule. So in the top, we have to distribute 4 times this 2-term expression. We have to distribute. If it helps you to see that, instead of a dot, you may want to use parentheses. Distributing this 4, we get 20 minus 4 square roots of 6. In the bottom, if I FOIL this out, the first, 5 times 5 is 25. The outside, minus 5 square roots of 6. The inside, plus 5 square roots of 6. And product of the last, minus, watch your signs, and square root of 6 times itself is just 6. In the bottom, we combine like terms. 25 minus 6 is 19. Minus 5 square roots of 6 plus 5 square roots of 6, they subtract out. And notice that my denominator then, because they subtract out, has no square root, which was our goal in rationalizing these denominators. As we work these from here on, I'm not going to FOIL. I'm going to use our special product rule. And I'm going to say, oh, well, this is just going to be the first squared minus the last squared. First squared is 25. Minus the last squared, you square the square root of 6, you get 6. Because I know that those outside and inside terms are just going to subtract out every time. A bit of terminology. These two guys here in the denominators are called conjugates. This plus that and this minus that are called conjugates of each other. That's a definition given to us here on page 692, toward the bottom, about 3 lines above that blue box at the bottom. It says x plus y and x minus y are conjugates. And it explains here again why we use a conjugate to rationalize a two-term denominator. So here at the bottom of 692, rationalizing a binomial denominator, I would prefer that said rationalizing a denominator of two terms. But it says, whenever a radical expression has a sum or difference with square root radicals in the denominator, rationalize by multiplying both the top and the bottom by what? The conjugate of that denominator. Let's do a few more. Number 86. We have two terms in our denominator with a square root running around. So let's multiply the top and bottom of this to rationalize this denominator by the conjugate. The denominator is 3 minus the square root of 3. My conjugate then is 3 plus the square root of 3. In the top, we'll need to distribute. In the bottom, we will use our special product rule that says the product, I can now say the product of two conjugates is the first squared minus the last squared. As we distribute in the top, we've got 3 square roots of 27 plus the square root of 27 times 3 is 81. Now, if you're paying close attention, you've already spotted that one way I could have started this problem, and probably should have started this problem, is simplifying square root of 27. 27 contains a 9. I could have rewritten square root of 27 as 3 square roots of 3. We'll end up with the same answer anyway. I want to concentrate on what we're doing here in these denominators. We're multiplying conjugates. So I will get what? The first squared, 3 squared is 9, always minus the last squared. Square root of 3 squared is just 3. Let me go ahead and start simplifying here in the top. That 27 is 9 times 3. Square root of 81 is simply 9. And then the bottom, 9 minus 3 is 6. Still working here in the numerator, I've got a 3 times square root of 9 is 3, and that other 3 is stuck inside. Do you see what happened? I took the square root of this 9 and it gave me this 3. Three times 3 is 9. So I have 9 square roots of 3 plus 9 all over 6. Am I done? Think about this. If we were back in chapter 6 and I had 9x plus 9 over 6, is that simplified? No. What would I need to do? I would need to factor out a 9 in this numerator and reduce. Factor out a 9 in this numerator and reduce. Well, I also want you to think about this. Instead of factoring out, couldn't I just say, there is a common factor of 3 in all of these terms. There's a common factor of 3 in all of these terms. So, if I divide the top and bottom of this fraction by 3, I'm dividing all of the terms by 3. Knocks that down to 3x, knocks that down to 3, knocks that down to 2. And so I would end up with 3x plus 3 all over 2. When you're reducing a fraction, you divide the top and bottom by whatever common factor you need to. What you're really doing is dividing all of the terms by that common factor. Let's do that here. 3 goes into 9 3 times. 3 goes into 9 3 times. 3 goes into 6 twice. This is not a 3. That's a square root of 3. That 3 is an insider. He can't see what we're doing as we reduce this fraction. This is now simplified. And again, like I said earlier, we could have started by rewriting this square root of 27 as 3 square roots of 3. We would end up with the same answer. My focus here at that moment was, let's deal with those conjugates in the denominators. Let's do a couple more. Number 88. I hope you enjoyed section 10.4 while it lasted. I told you this one was going to take a little more work, but it's really not that bad. Some practice and you'll be doing these just fine. We have 2 terms in the bottom. So we need to multiply the top and bottom here by the conjugate of this denominator. 3 square roots of 2 plus 2 square roots of 7. In the top, we distribute this negative 1. And that simply gives me minus 3 square roots of 2 minus 2 square roots of 7. It's just distributing a negative. Now in the bottom, you could FOIL this out if you want. I'm going to use our special product rule and say it's the first squared minus the last squared. The first squared, you square 3, you get 9. You square the square root of 2, you just get 2. Always minus. What goes here? Square 2 square roots of 7. You square the 2, you get 4. You square a square root, you get what's inside. So squaring the square root of 7 just gives me 7. Let's clean that up. Nine times 2 is 18. 4 times 7 is 28. And 18 minus 28 gives me minus 10. Now notice here that all of my terms are negative. It is generally best practice Although I would count this right if you put a box around this. It is in lowest terms. But it is generally best practice when everybody is negative. Multiply the top and bottom by -1, or if you want to call it, divide the top and bottom by -1. That is, change the sign on every single term, or think of it as canceling a factor of -1 out of every single term. And if you check in the back of the book on a problem like this, this is most likely the way you will find that answer. All right, number 94. We have two terms in the bottom. To rationalize this denominator, we'll multiply the top and bottom by the conjugate of this denominator. Three square roots of r now minus square root of s. In the top, we will distribute. As we distribute, 5 and 3 are both outsiders, so we'll get 15 square roots of r and minus 5 square roots of s. In the bottom, yes, you can FOIL that, but it's easier to get used to using that special product rule. It's faster. It's going to be the first squared minus the last squared. The first squared, you square the 3, you get a 9. You square the square root of r, you get just r. Always minus, and the last squared. Square the square root of s, you get just s. Is there anything else I can do here to simplify this further? I suppose you could factor a 5 out of the top. And a lot of times in these problems, your final answer in the back of the book will be shown in factored form, because you're checking for lowest terms. But honestly, what I showed you with that pink fraction a minute ago kind of makes it unnecessary to factor out greatest common factors. If you look it up in the back, you may find this form of the answer. I have no problem, and in fact I prefer where we ended up. If there had been a factor of 5 in all 4 of these terms, 2 in the top, 2 in the bottom, I would have canceled them. When you look this up in the back, if you find this, just be able to compare your answer to hers and say, yeah, I got the right answer. Almost done, guys. We are on the home stretch. I've got 2 more problems I want to work for you this semester. Number 100. All she's doing in these problems is saying, let's practice writing in lowest terms. Let's practice simplifying these. This may be like a result that you would get from one of the previous problems, but is it in lowest terms? One way to work this problem, but I want you to get used to that other way. One way to work this problem, I can factor a 12 out of the top, which would leave me 2 plus the square root of 5. Not sure, distribute it back in. It returns you to the previous step. And over 12. Those 12s will cancel. And so this is 2 plus the square root of 5. What I would prefer is that you get comfortable with saying, hey, every single term here contains a factor of 12. If I divide the top and bottom of this fraction by 12, I'm dividing every term, top and bottom, by 12. 12 goes into 24 twice. 12 goes into 12 once. 12 goes into 12 once. And I don't generally write those ones because they don't do anything. And so what do we have? 2 plus square root of 5, what? Over 1, but we don't write over 1. This is a very handy process to become accustomed with and get used to. It'll serve you well in your next math class. And finally, the last problem that I will work for you in lecture this semester, number 106. And just in time, because my marker's about gone here. All she's asking us to do in these problems is reduce to lowest terms. But in order to check this for lowest terms, I need to deal with this radical. This radical contains some perfect square factors. 242. Do you spot that it contains a 121? 242 is 121 times 2. 121 is the square of 11. Y to the 5th contains y to the 4th, along with one other factor of y. So, simplifying the second term of the numerator, square root of 121 is 11. Square root of y to the 4th is y squared, leaving the 2y inside. And now that we have that done, we can check for lowest terms. There are 3 terms in total here. The 11y, the minus 11y squared square roots of 2y, this whole thing is a term, and our single term here in the bottom, 22y. What do they have in common? And I'm going to need to make some room here, guys. What do they have in common? Every term contains a factor of 11. So if I divide the top and bottom by 11, I'm dividing every term by 11. 11 into 11 once, 11 into 11 once, 11 into 22 twice. What else do I see? Every term contains a factor of y. Now remember, I'm only looking at outsides. Insides can't see outsides. So this 2y, he's just hanging out by himself. Every term here, though, contains at least one factor of y. Divide the top and bottom of this fraction by y. That is, divide every single term by y. Y goes into y once. Y goes into y squared, leaving a single y behind. And y goes into y once. And so, what do we have? Well, this term we canceled everything, so what's left behind? A 1. Minus, what survived here? That y on the outside, and of course our square root of 2y just hanging out, doing whatever he's doing. All over, and in the bottom, just a 2. So in this problem, first we had to simplify one of our radical terms before we could go on simplifying our fraction by reducing it to lowest terms. So guys, that's our look at section 10.5. That is our look at chapter 10. Hey guys, just a quick edit. I realized I could not leave this last problem with its answer unboxed. I would never hear the end of it. So there. That finishes our lecture videos.